Good day, everyone. Once again, we meet, and today I want to take you through a rate of reactions. Obviously, this is under our subject of chemical change. I've gotten quite a number of requests on this section, and it's been something that I've been wanting to cover with you. Now, my approach is going to be a little bit different today, as much as I want to go through the voluminous amount of explanations about the theory part and all of that, but I just realized that that could take us quite a while. So my thoughts were that I'll just cover the theory briefly, and thereafter just quickly delve into the question. I don't want you falling asleep in the process of watching this video. So I hope that you enjoy it. Okay, if you haven't subscribed, please do so. Just make sure that you hit that bell button so that you can always get notifications when we've got a new video that's coming. All right, ladies and gents, and if you need to get in touch with me, please, my email still remains. That's mlungisi.m.ngosi@gmail.com. That's MLUNGISI .m for Mary .nkosi.com. All right, let's get into it. So when we talk about rates of reactions, or rate and extent of reactions, what exactly what does it entail? So first of all, I want you to notice there's just some things that we need to understand about what does it take for a reaction to take place, right? So in this case, we've got what we call the collision theory, okay? And the collision theory simply states, or let's just write it down there. So the collision theory simply tells us that in order for any reaction to take place successfully, right, there's a requirement. First of all, particles must have sufficient kinetic energy. Particles must have. Now, what do we mean that sufficient kinetic energy? It means that kinetic energy must be greater than what we call the activation energy. Now, what is the activation energy? That's the minimum energy required in order for a product to be formed, in simple terms. So that's the minimum energy required in order for a reaction to take place. So in this case, so in order for any reaction to be a successful reaction, that is, in order for products to be formed, we must make sure that particles have got sufficient kinetic energy. That's kinetic energy that's greater than the activation energy. And secondly, we say that they must have a correct orientation. Correct orientation, okay? Right. Now, if these two conditions are met, then we know that this results in what we call an effective collision. So a combination of these two together results in what we call an effective collision. What is an effective collision? Well, it's a collision whereby products are formed, or that results in products being formed. So an effective collision takes place. Now, in this case, so we say this is what the collision theory entails, right? So in a sense, we want to make sure that every time that a reaction takes place, of course, what we want to happen is that we always want reactions, or we always want collisions to be successful, isn't it? To be effective, so that products are formed. Now, there's a way in which we can speed up the formation or the production of products. In this case, this is where the whole thing about the rate of reaction comes in. Because how do we measure the rate of a reaction? In fact, what do we mean when we say rate of reactions? Well, we say this is the number of moles, okay, of products formed per unit of time. Or you can say this is the change in the amounts of products formed per unit of time. Or you can even use reactants, right? because remember, you use reactants to form products. So it could be also the change in the amounts of reactants used per unit of time. Okay, so in this case, how do we improve the rate of a reaction? Okay, so we say that there are 5 factors that affect the rate of a reaction. All right, I'm going to actually exclude one of those factors. Okay, they don't ask about it much. So we say that there are 5 factors that affect the rate of a reaction. All right, so the first factor is concentration. Okay, so right, so the first factor that improves the rate of a reaction is concentration. All right, now if you want to think about it, when we talk about concentration, we are talking about the number of moles, okay, that are there per unit of volume. So if you take, for instance, say maybe there's beaker A and beaker B, okay, so that's A, we close it there, and we've got beaker B, assuming that they are equal, right? So if I've got more particles of gas here, all right, within this beaker, in this case, there is a higher concentration of that particular gas per unit volume. So if the two volumes are equal, so in this case, this is more highly concentrated, right? Now think about it. Why would concentration increase the rate of a reaction? Okay, so the higher the concentration, the more particles there are, right, the more chances of collisions taking place per unit of time, isn't it? Right? So it means more collision take place, right? So in this case, it would result in the rate of a reaction. So obviously, if more collisions are taking place, there'll be more chances of effective collisions taking place, right? Per unit of time. And then the second factor, we say it's temperature, right? So the next factor that affects the rate of a reaction is temperature, right? Now, what is temperature? It's the measure of the average kinetic energy. Now, think about it. In any particular, for any reaction to take place, we said that the particles must be moving, isn't it? So in this case, they must be moving with a kinetic energy that's greater than the activation energy. So what we're simply saying, when you increase the temperature, you are causing them to move even more, right? It means their average kinetic energy now becomes higher, and as a result, because there's more movement, then in that case, there's more collisions per second, and as a result, that would increase the rate of the reaction. I hope I'm summing it up quite nicely, right? And then the next one, we say that it is, so we said it's concentration, it's temperature. Well, the third one is pressure, okay? Now, in pressure, I want you to think about it. Like this would actually affect gases, okay? Just remember that. And by the way, can I just say this whilst I'm at it? When I talk about concentration, remember that concentration only is applicable when it comes to gases and aqueous solutions. Aqueous solutions, right? So in this case, once it's a solid, remember that you cannot define it in terms of concentration. I want to get into those details, but as I said, I don't want to bore you too much. I want to get into past exam questions as quickly as I possibly can. Right, so in this case, when we talk about pressure, so when I increase the pressure, what am I doing? I'm actually decreasing the space. Say maybe this was my container, and now I increase the pressure. What am I doing? I'm going to now decrease the space that is there. So what happens? The particles get closer together, right? And think about it. Now, the closer they are to each other, the same thing would happen when we had a higher concentration, right? So the closer they are, the more frequent the number of collisions take place per second, and as a result, the rate of reaction would also increase. And then we also have surface area, okay? So surface area, or sometimes they talk about the state of division, right? So what do we mean when we talk about state of division? So in this case, state of division, it's when you break something down into smaller pieces, right? So you can imagine, normally if if I was to take something which is in a chunk form, say maybe I'm taking a tablet, okay, a Disprint tablet or whatever the case may be, and I put it inside an amount of water, and I want it to dissolve, right? Of course it would dissolve over time. But now think about it. What would happen if I were to crush it before I dissolve it? Okay? Right. You agree with me that it would actually dissolve faster when I've actually divided it more, right? So in this case, when you break something into smaller pieces, in this case, what it does is that it tends to increase the rate of reaction. Right. Even when we talk about surface area, this is when we are talking about usually those would be reactions that are that are in a state of that are in different states, right? So in this case, if I were to take something that is perhaps in a solid state and liquid, there's a word I'm looking for. It's just slipping my mind. Right, something that's in a liquid state and a solid state. In this case, the one that is solid, if I can make it spread it out a little bit more, okay, it would increase the rate of reaction. In fact, I want you to just think about it. Normally, when we want to cook an egg, right? If I were to take an egg and I boil it in water versus an egg that is fried, okay? I don't know how to draw an egg. So there's an egg. I were to fry it. Right, which one cooks faster? Definitely it would be the one that is fried, right? But why is that? Because this one is actually more spread out. So heat tends to reach more of the egg quicker than this one that is boiled, right? Because heat can only be on the outer surface, and it can go in gradually. So in this case, we say that surface area does increase the rate of reaction. All right. Okay, and then the last one, it's the addition of a suitable catalyst. Okay, now, ladies and gents, we've got two types of catalysts. Okay, we've got what we call positive catalysts, and these are catalysts that speed up the rate of a reaction. Okay, so in this case, when you add that catalyst, what is a catalyst? Let's start there. Okay, so we say catalyst is a substance that speeds up the rate of the reaction without itself undergoing any permanent change, right? So a catalyst can speed up the rate of a reaction without necessarily participating in the reaction per se. Okay, so it doesn't undergo any permanent change, or it does not undergo any chemical change for that matter, right? And then we've got another type of catalyst, which is a negative catalyst, which is called an inhibitor, right? So what that catalyst does is that it slows down the reaction, okay? And basically, how does a catalyst actually work? What it does is that a catalyst would lower the activation energy of a reaction, okay? Now, I want you to imagine this, okay? So if we lower the energy that is required for the reaction to take place, right? Now, all of a sudden, it means that more particles now possess sufficient kinetic energy, and therefore it means that more effective collisions would take place. Okay, so what a catalyst does is that it lowers the activation energy. I want you to remember that, right? Or it decreases the kinetic energy. All right, so it lowers the activation energy. Did I say kinetic? Right, it lowers the activation energy of a reaction. So it lowers the minimum energy required. So I want you to imagine this. If, let's say, they said we are forming a club, right? and people are going on trial. You know, they are going to try out for, you know, entry into the club. If they say, okay, it's a running club, let's say, for argument's sake, we want top runners, and they say, in order for you to qualify to be part of this club, you have to run 100 meters in less than 11 seconds. Okay, I'm just making an example, right? You agree with me that not too many people would make it, right? Now, what if they now lower the minimum entry and they say, okay, in order for you to be accepted, you have to at least run 100 meters in 15 seconds. You agree with me that because they've now lowered the bar, it means more people can qualify, isn't it? Right? I want you to think of it that way about a catalyst. What it does is that it lowers the activation, the minimum energy required, so that now more reactants now would possess sufficient kinetic energy, and so as a result it means that the number of effective collisions would take place. All right, it would increase the number of effective collisions, and so that is how the rate of reaction would be increased. Okay, right. Now, ladies and gents, what I quickly want to talk about are some of the graphs that are required for rates of reactions, because one thing or the other, you will always encounter those questions. Okay, so now we've got two types of reactions that take place. Okay, all right, maybe let me just write it over this side here. Okay, we've got reactions that are referred to as endothermic. Okay, endothermic reactions. Right, now in an endothermic reaction, I want you to just notice the type of graph that we are going to have for an endothermic reaction. Sorry about that. Okay, let me just bring this down a little bit. Right, so in an endothermic reaction, what type of a graph am I expecting, right? So we've got a graph that shows us, now notice it's going to show us the heat of the reaction, or the enthalpy of a reaction, okay, against what we call reaction coordinates, or the extent of the reaction. Okay, so this would be the heat of the reaction, or the enthalpy, or the energy of a reaction. Okay, versus in this case what we call the reaction coordinates. Okay, reaction coordinates. So coordinate, goodness, I'm just making a holy mess here. Coordinates, there we go. Right, so in this case we're saying, for an endothermic reaction, how would you realize that? Now, as I said, ladies and gents, I really don't want us to go too much into the extent of the reaction. For me, all I want you to do is just possess just that minimum that you need for now, and then we'll delve into more questions as we answer our past exam questions, right? So for an endothermic reaction, what happens there? So we're going to have, normally for an endothermic reaction, you're going to have a graph that looks like this. Okay, so whereas this is showing us, okay, let's say this is a reaction between two things. We're going to have A plus B giving us AB, right? So if this is a reaction between two things, A plus B giving us AB, so this is the part where we've got A plus B as reactants. Now you can tell the energy here, right, is lower than the energy there. So this is the portion where now we've formed products. Okay, so in an endothermic reaction, it simply means that we now, or rather the products need to absorb energy in order to form products. Okay, so the reactants need to absorb energy in order to form products. Now, several things that I want you to note in this graph. The first thing that I want you to note is that this energy here, okay, so between the reactants and what we call the activated complex, okay, so this is the temporary state. It's an unstable state. So this is when, you know, after they are colliding, they have high energy and they are temporarily unstable just before they form products, right? So at this state here, so we call it the activated complex, okay? So this is the activated complex, right? This is the state there. So we're saying in order to get there, we need to put in a high amount of energy. So this is the activation energy for the forward reaction. Can you see? For an endothermic reaction, it would be a high amount of energy that's required, isn't it? So in this case, so this is the activation energy for the forward reaction. And then you look at this. So we say, okay, this is the energy of the products, okay? I'm getting somewhere with this, right? So this is the energy of the products. Now you can see for an endothermic reaction, the energy of the products would be higher than that of the reactants, isn't it? So where do I get the activation energy for the reverse reaction? So this is EAR, okay? So I'm just going to designate it EAR there. Sorry about the mess that I'm making. Right, so in this case, we're simply saying that is going to be the activation energy for the reverse reaction. Now, ladies and gents, I want you to please note, why am I showing you all of this? Right, so now we get to this part here where it's the energy of the products, right? So this is the energy of the products. This is the energy of the reactants. This is the energy of the reactants, right? So then we start defining what we call the change in enthalpy, delta H, right? So we say change in enthalpy is simply going to be the energy of the products minus the energy of the reactants, right? So I want you to please notice here, we've got a higher value, whatever that value would be, right? Let me just show you that this is delta H there. So whatever this energy would be, you agree with me, is higher than that that energy there. So this value minus that value, it would always give you a positive result, okay? So for an endothermic reaction, you've got delta H that is greater than 0, or you can just simply say delta H is positive. So they may give you delta H is equals to positive whatever the value may be, right? So immediately when you see that delta H is greater than 0, what it's simply telling you is that the energy, or rather the reaction absorbs, the reactants rather absorb energy in order to form products, okay? Right, so then we've got what we call an exothermic reaction, okay? I'm just going to write it down there. You can tell I'm trying to rush as much as possible, right? As I said, I don't want you getting bored before we get to the crux of it, okay? I'm just going to open up a little bit more space here, okay? Right, so for this reaction, what we have is that for an exothermic reaction, you would have something like this, okay? So let's say we've got another reaction, A plus B giving us AB, okay? Right, so for an exothermic reaction, I want you to please note, this is where we've got A plus B, so this is going to be our reaction, our reactants there, all right? And then look at this, the activation energy that you require, okay, is actually less than when you compare it, let's say, with a with an endothermic reaction. So this is the activation energy for the forward reaction, right? And then this is when you've formulated products, and then what do you notice there? All of a sudden, this is the activation energy that you require in order to form, or rather, this is the activation energy of the reactants, okay, of the reverse reaction rather. So in this case, look at this: the products have got less energy than the reactants. Okay, so what we are simply saying in this case, we're simply saying in an exothermic reaction, you find that there is a net loss in the amount of energy in the reaction. Okay, so as a result, what do we notice? We notice that again, if we calculate that delta H value, the energy of the products minus the energy of the reactants, so that's delta H, that's the change in enthalpy, right? So we find that if we find delta H, okay, it will be the energy of the products again minus the energy of the reactants. Okay, so what do you notice? Products have got less energy, so it's a lesser amount minus a greater amount. So yes, that sets us up now to get a negative result. So that is why we'll get delta H less than 0. So it means that what you'll find in this reaction, so when it's you find that energy is released. So when it's an exothermic reaction, say maybe if you were conducting this reaction, one of the examples is that of a combustion when you start a car. All right, so after a while you'd feel that the engine of the car gets warmer, isn't it? But why is that? Because when the octane in the car, all right, reacts with the oxygen, right, it forms carbon dioxide, it forms water, but it also releases energy. All right, so that is why you find that the engine ends up being warmer, of course, besides all the other factors, mechanical factors, which I won't talk about much today. So the net result of that reaction releases energy, and so that is why it tends to get warmer. It's energy that is released together with the products. On the other hand, for an exothermic reaction, it's energy that is absorbed. So you'd find that when this reaction takes place, the reaction as it takes place, the container or the vessel in which you are conducting the reaction in gets colder. So why is it getting colder? Because it's actually absorbing energy from the environment. Okay, so as a result, we know that it is actually an endothermic reaction. Okay, so those are the factors that affect the rate of a chemical reaction. Now, just one thing that I want you to notice, ladies and gents. So what happens in these reactions when we now add a catalyst? You remember what we said a catalyst does? We said it lowers the activation energy, right? So in this case, when I add a catalyst, I want you to note we'll still get the same graph, but you'd notice that the actual peak, the activation complex, takes place at a lower peak. Now I want you to note this red graph is a graph that shows us when we've added a catalyst. So when I add a catalyst, by the way, I'm going to say use catalyst generically, but when I say catalyst, I mean a positive catalyst in this case. Okay, obviously a negative catalyst would do the opposite, but all right, let's not focus on that much. So when I add a catalyst, it's going to lower that peak there so that the activation energy now is much lower than what it was. The same thing happens even for the one for the endothermic reaction, right? When I add a catalyst, it lowers that activation energy, okay, so that peak is much less. Okay, right. So in terms of the theory, okay, I still want us to continue. All right, yeah. Now let's move on to something else. So we have what we call the Maxwell Boltzmann distribution, right? So just to explain that quickly, ladies and gents. So this is a graph that shows us Okay, let me just try and draw that graph quickly. So this is the graph that shows us in a sense, you wanna imagine, the number of particles. So imagine in a reaction, so many collisions are taking place. So it shows us the number of particles that are colliding in a sense, okay, against the kinetic energy of the molecules. Now, just something I want to, okay, so this is the number of particles. So number of particles that are colliding, okay, against their kinetic energy. So this is what we call the Maxwell, okay, all right, let me just adjust there a little bit, okay. So this is the Maxwell Boltzmann distribution. Boltzmann. Okay, right, so this is the Maxwell-Boltzmann distribution, right? So this distribution is actually a statistical distribution curve. For those of you who've done stats, okay, you'd see this is a bell-shaped curve, right? Just to make you understand quickly what's happening on this curve, right? So if you think about it, we spoke about temperature, right, being the average kinetic energy of a molecule. Now, let's say these are particles that are at temperature, at a particular atmospheric temperature. Let's say the temperature around says 25 degrees, right? But what you'll find is that the number of particles that are there have different kinetic energies. Now, you see, you'd find that there's less of them that have a lower kinetic energy, all right? So this one shows us the average kinetic energy. You remember we said that temperature, right, shows us the average kinetic energy, so that would be the average there. But let me just quickly get to something. So this one here is what we call the activation energy. Now, let me just explain quickly. So it means any number of particles that have the energy, their kinetic energy greater than this minimum here. Anyone that crosses this line would then be able to form what we call effective collisions. So all of the particles that are below here are not able to form what we call effective collisions. So it means they're able to collide, but those collisions don't result in products being formed. It's only these ones that have this amount of energy and more that are able to form what? Effective collisions that can form products. Okay, so these are effective collisions. Now, look, ladies and gents, I don't know if I want you to spend as much time on this one here, but let me just explain something quickly about the Boltzmann distribution. Now, let's say temperature 1 gives you that temperature there, okay? I mean that shape of a curve. What if I give you the same reaction but at a higher temperature? What happens? So when I raise the temperature, well, I'll still get the same thing, but I want you to please note what happens, okay? So this is what happens when I increase the temperature. Note what has happened. So it means this curve here that is at temperature T2, where, by the way, I am actually saying that the temperature T1, or rather temperature T2, is greater than temperature T1. Now, all of a sudden, what happens to the distribution? Well, the distribution widens up. First of all, your distribution, your graph gets wider. And then notice the peak of that curve got lower, right? Sorry that my graph is not really the best. And then secondly, what happened? The average kinetic energy. Do you see that it's shifted now? My average is right here now. Okay, so when you increase the temperature, it increases your average kinetic energy, and as a result, because your average has increased in that case, all right, now I want you to note, we said this is our activation energy here. So now when I increase temperature, can you see that more particles now are able to have effective collisions, that area there has become greater, right? So in this case, it means that more particles are able to have effective collisions, all right? So here's our kinetic, we said that's our average kinetic energy. So that's EK average, né? Right? But when we've got temperature 2, which is greater, our average kinetic energy is now much higher. All right? So as a result, ladies and gents, as I said, I don't want us to spend as much time on this, right? But nonetheless, I want you to know how to explain it, and I want you to know how to make your argument, to know the difference when they give you different types of distributions or shapes, right? And then just one last thing. What happens when I add a catalyst? Remember, you remember what we said about a catalyst? We said what it does is that it decreases this value here. So if that was my minimum kinetic energy required, so a catalyst would now shift this value here. Now what happens? When I shift the kinetic, when I lower the activation energy, by the way, when I lower that activation energy, it means now more particles are able to react. Okay, right. Now, here's what I want us to do, ladies and gents. I know that this is quite a big chapter. I know that it has quite a lot of things that I can explain. But what I want us to do is just to try and delve in as much past exam questions as we possibly can, and then what I'll do is that I'll explain some of the things as I answer questions. I hope that's fine with you, right? Okay, let's get into it. All right, so I take this question from the March-April paper of 2020. This was for the senior certificate exam, but I'm sure you can get this paper somewhere else. Let's try and look at what this paper, this question entails. So they say we've got 2 experiments that are carried out to investigate one of the factors that affect the reaction rate. You remember we've got 5 factors, right? Between magnesium and dilute hydrochloric acid, right? They say the balanced equation below represents the reaction. So they've given us the reaction. They say in experiment 1, a certain mass of magnesium ribbon, can you see, reacts with excess dilute hydrochloric acid. Now, ladies and gents, I know I haven't gone through this with you yet, but I want you to note, once they tell us something is in excess, then it means that the other one immediately becomes what we call the limiting reactant or the limiting reagent, right? So it means the other one that is not in excess is the one that's going to actually limit the extent of my reaction. So it means it's going to run out first, right? And so if it runs out first, it's going to determine the amount of products that I'm going to form. Okay, right, now let's continue. Okay, they say in experiment 2, magnesium powder. Now notice what they've done. In experiment 1, they used magnesium ribbon. Can you see? Right? And in the next one, they used magnesium powder. Right? So in this case, what they are simply doing, they are changing something between the 2 reactions. Okay? Now, of course, we should already note that the one that's in powder form, what have they done? They have now divided it up even more. They have changed what we call the state of division. All right? Right, so they say magnesium powder of the same mass as the magnesium ribbon, right, reacts with the same volume of excess dilute hydrochloric acid. The concentration of the acid is the same in both experiments. Now, let's get into it. They say the apparatus below is used for the investigation. So there's our apparatus, okay. Of course, the Americans would say apparatus. Okay, so there it is happening there. You can see some gas bubbles forming. But why are those gas bubbles forming? It's because we are also producing, or rather we are producing hydrogen gas there. Okay, right. Now, they say for this reaction, define reaction rate. Remember, we said it is the change in the amount of products formed per unit time, right? Okay, so it's the change in the amount of products formed, or you can say it's the change in the amounts of reactants used per unit of time. Okay, and then they ask us this very important question. They say for this investigation, write down the independent variable. Ladies and gents, I want you to please note, what is an independent variable? So between the two reactions when they took place, we've got experiment 1 and experiment 2. There's something that we changed in the two experiment, isn't it? What is it that we changed? Right? Remember, in the one we were using magnesium ribbon, right? And then in the other one we were using magnesium powder. So what did we change? Everything else remained the same except the state of division of what? Magnesium. There it is. So in this case, what we changed between the two reactions is called our independent variable. What did we change? The state of division of magnesium. All right. So our independent variable is the state of division of magnesium. Now, I know they didn't ask us this, but let me just say it whilst I'm at it. So what would be my dependent variable? Now think about it. When I change the state of division, it affects the rate of reaction. So it means that rate of reaction, okay, would be my dependent variable. And please, I want you to always note, when we're doing rates of reactions, rate of reaction, okay, would be my dependent variable all the time. Okay, now, and then they ask us, write down the control variable. Now, please, I want you to note, we've got several of them. Okay, I suppose in this case they want you to actually just write one control variable. But think about it. What is a control variable? It's something that you need to make sure that you keep the same. Now, in order for this to be a fair test, in order for it to be a fair experiment, a fair test between the two, you only have to have one independent variable. So what do I mean? If we've changed the state of division, one we are using ribbon and in the other one we are using powder, right? You can't then have powder here plus a higher temperature. Okay, so there needs to be only one thing that is different between the two, so that when we make our conclusion, we know for a fact that it's definitely the state of division that affected the rate of reaction. Okay, so control variable would be something that stays the same, okay, between the two reactions, right? So what stayed the same? I'm sure you've guessed it by now. We saw how they actually told us it's the concentration of what? Hydrochloric acid, right? What else? It would be the volume of hydrochloric acid. What else can we keep the same? It could be the type of beaker that you use, right? What else can we keep the same? The temperature at which you conduct the experiment. You need to definitely make sure that you keep those the same. So in this case, you can mention any of those. And if you are able to think of more examples, you are more than welcome, ladies and gents. Right, now, let's get to the next part of our question, right? Now, they say to us, the change in mass, okay, of magnesium is calculated and recorded in 2 minutes, 2-minute intervals for both experiments. Okay, so here's the graph. The results obtained are shown in the graph below, and it's not drawn to scale, right? So now, what is this change showing us? The mass of magnesium. Obviously, magnesium is reacting. You remember that, no? So magnesium is reacting, and what is it forming? It's forming magnesium chloride, and it's also forming hydrogen. So obviously, as it reacts, what would happen to the mass of magnesium? It would actually decrease, right? So it means that the mass of magnesium would keep decreasing until, remember, it's our limiting reagent, until it runs out, right? So the experiment would stop immediately when we run out of magnesium, okay? Right. Now, this is for experiment 1. I want you to notice something. So this is the magnesium decreasing, the mass of magnesium. And why is it decreasing? Because it keeps reacting and reacting. So you are forming less and less, or rather you have less and less magnesium until it becomes 0. And it does so after 16 seconds in experiment 1. But then in experiment 2, you remember we had magnesium powder. Okay, so what happened? Of course, I'm expecting that the one in powder would actually get to completion much faster, isn't it? So in this case, look at it. It's decreasing. It's got a very sharp decrease, and in this case, it reaches completion at 10 seconds, right? So it's actually 6 seconds less than the first one. So in this case, what is it showing us? It's showing us that when we increase the surface area, or when we increase the state of division, then it obviously increases the rate of the reaction. Now let's get to the question quickly. Right. Now what do they say to us? They say use the information in the graph, right? Calculate the volume of hydrogen gas produced in experiment 1. Okay. Right, so we're going to use the information in the graph, all right, to calculate the volume of hydrogen gas produced. Right, at some point or the other, I'm going to make a video on stoichiometry because I really think that it is an important part of what we must know, right? Right. They say to you, take the molar volume, the molar gas volume to be 25 cubic decimeters per mole, right? So there's our molar volume there, that is Vm. Right, so how do we conduct this, this question? Okay. Right, so one thing that I want you to notice is that we are now looking at the volume that is produced, but not just at any particular place. They did say specifically from t is equals to 2 minutes, so from that point there to t is equals to 10 minutes, okay, which is that point there. And they specifically said for experiment 1. So now let's look at it from the graph, okay? I want you to please stay with me, ladies and gents. So now, experiment 1, what is the volume, or rather, what do we know from the graph? We know that the mass of zinc at 2 minutes, right, was 2,6, and the mass of zinc at 10 minutes is 0.2. So what is the amount, what is the mass of zinc that was used between those minutes? So the mass of zinc, sorry, did I just say zinc? Magnesium, sorry about that. So the mass of magnesium in this case would be the change that took place between those 2 points. So it would be 2,6, okay, minus 0.2. So that's the amount, or that is the mass that we actually used, right? So that's 2.6 minus 0.2. That would give us 2.4 grams, okay? Now, ladies and gents, I want you to please remember we were given the reaction. Okay, I'm just going to flip over to that page there. They told us that the reaction takes place in this manner. We've got magnesium plus 2 moles of hydrochloric acid. Okay, that gave us magnesium chloride, MgCl2, plus H2. Okay, right. So we want to find out about hydrogen. Now, what is going to limit the extent of our reaction? Remember that what limits the extent of the reaction is going to be the magnesium, isn't it? Is it possible for me to get the number of moles? And now, please, ladies and gents, you do not conduct stoichiometry based on mass, all right? But you always need to now reduce it to number of moles, right? Is it possible for me to get the number of moles of magnesium? All right, so I'll then say, okay, yes, it is possible. So I've got number of moles. Remember, these are the number of moles of magnesium, right? This is equal to mass divided by molar mass. Of course, I'm assuming that we would have done this in grade 10, grade 11. So we're quite familiar with it, okay? Just remember, ladies and gents, for those of you who are doing, either the SCE exam or the senior certificate exam, or who are writing the final exam in November, okay, those who are doing the national senior certificate, you are given these things, okay? You are given these at the back of your question paper all the time. You've got your periodic table there, you've got your standard reduction potentials over there, and then you've got your formulas over there. So I'm just going to take our formulas quickly, right? Remember that you have all of these things. So I'm using this particular formula. Number of moles is mass divided by molar mass, right? But what am I looking for? The number of moles of magnesium. So then I go to my periodic table and I say, okay, what is the relative atomic mass, okay, of magnesium? What is the molar mass of magnesium? Can you see there? That's 24. So in this case, to get the number of moles, I'm going to say this is 24 divided by 2.4 rather. Sorry about that. So this is going to be 2,4 divided by, what is my molar mass? This is 24, right? And now obviously this is going to give us a value of 0.1 moles. Now stay with me, ladies and gents. Right, so that is the number of moles of what? Magnesium. Okay, so that is the number of moles of magnesium. But that's not what I was asked. Remember the question, right? The question said to us, calculate what? The volume of hydrogen. So what we want to find out is how much hydrogen was formed at the end, right? Now please follow me carefully. Now the formula that we have says for any number of moles, remember these stoichiometric coefficients, these coefficients here, there's a coefficient of 1, right? It says for every 1 mole of magnesium, I will actually produce how many? 1 mole of what? Hydrogen. Okay? So it simply means for any number of moles of magnesium that I use, remember you can only use moles with this. That's why I needed to find this out first, right? So for any 1 mole of magnesium, I will produce 1 mole of hydrogen. So it means if I've got 1, I produce 1. If I've got 10, then I will produce 10. If I've got 0.1 mole, then I will produce 0.1 mole. So therefore, it means that the number of moles of hydrogen that will be formed should also be equal to 0.1 moles. Why is that? Because it is a 1, or there is a 1:1 ratio between the two. And remember, ladies and gents, you can only do this once you've got that as number of moles. With gases, I suppose you can also do it with volume, but we'll talk about that another time. Okay, right. So now we've got the number of moles of hydrogen, right? Okay, so now that we know the number of moles of hydrogen, they told us that the molar gas volume, right, is 25 cubic decimeters per mole. So now we've got another formula. Let me just show you quickly, right, that relates volume of a gas and the molar volume. So this simply says, okay, and I know I could have used also ratio and proportion, right? This formula here, it says number of moles is volume divided by molar volume, right? Okay, so, and the question was asking me to calculate the volume. So now I'm going to find the volume, right? And I've got the molar volume and I've got the number of moles. So now I'm going to simply say, so number of moles, this is going to be volume divided by molar volume. Right, now number of moles is 0.1. Okay, I want the volume, so I want the volume there, and I was given the molar gas volume to be 25. Okay, if they had said STP, by the way, we know that the molar gas volume at STP, that value there, right, that's the molar gas volume at STP is 22.4. But obviously this is at a different conditions, so they said it is 25. And all we need to do, ladies and gents, is just simply say 0.1 times 25. This would become 2.5 cubic decimeters. So the volume of hydrogen that would produce would be 2.5 cubic decimeters. I hope that made sense. All right, let's go to the next question. Right, now the next question simply says to us, they say calculate the initial mass of magnesium. Remember, we didn't have that initial mass. Okay, if you note in our graph there, that initial mass is there. Okay, right, I've written it as X there. Okay, but so we didn't know what that initial mass is. Okay, so they say calculate the initial mass of magnesium, right, used if the average rate of reaction of formation of hydrogen gas rather in experiment 2, so now we're going to this experiment here, okay, is 2,08 times 10 to the power minus 4 moles per cubic decimeters. Now I want you to please notice here, they have given me the rate of reaction in moles per second. Now please, I want you to stay with me. All right, so it means that I'm going to say, okay, I know rate of reaction. So the rate of reaction is always equal to the change in the amount of something divided by the change in time. I want you to please remember, whenever we talk about rate, okay, it's the change in the amount, okay, of either products or reactants divided by the change in time. Now please, let's realize, they said there we want the initial mass of magnesium, but they gave us the average rate of reaction, right, for the formation of hydrogen gas. All right, I want you to please note that. So, and they gave me that in moles per second. Okay, and by the way, they gave me for the full extent of the reaction. We'll come back to this. So it means that the rate that I want must be in moles per second. And you must remember, that's the rate of hydrogen. Okay, that's the rate of formation of hydrogen. So now it means it must be the change in the number of moles divided by the change in time. Okay, now I've got the change in moles, right? What is my change in moles? They gave me that as 2.08 times 10 minus 4. Okay, right? And then what are my moles? So when I say change, it's always going to be the mole final minus the number of moles initial divided by time final minus time initial, right? Okay, this is not moly. Okay, it's actually moles final minus moles initial. I just want to sensitize you to that. Right, so I want you to think about hydrogen. We were forming hydrogen, isn't it? Okay, so what were the number of moles that we had final? So what were the total number of moles of hydrogen that were formed? I don't know. Okay, so the mole final, I don't know. But what's the mole initial? Remember, when I start the reaction, there was nothing in terms of hydrogen that was formed. Okay, so in this case, I started with 0 moles of hydrogen. Now, let's look at our graph, right? Time final. When did that occur? It occurred at 10 seconds for experiment 2, right? And then my initial time, obviously, when I did not have any amount of hydrogen, that was at 0. Okay, right. So all I'm simply going to do, ladies and gents, is just some simple mathematical gymnastics, right? And as a result, just to get the number of moles, remember these are the number of moles of hydrogen. Okay, so now you just cross multiply. Obviously, this is going to be moles final over 10 and multiply that by 10. So the number of moles final, okay, so the number of hydrogen moles that I had would be 2.08 times 10 minus 3 moles. Okay, some of you obviously can express that in decimal form, which is 0.00208. Okay, right, so I'm just going to express it in exponential form. Right, now this is what we also want to do now. We know how many moles of hydrogen we formed, right? But that's not what we were asked. What was asked of us is to calculate the initial mass. So do you agree with me that if I were to know the number of moles of hydrogen that I formed, right, it would actually, because I know how my reaction goes, if I can know how many hydrogen moles were formed, I would be able to know the number of moles of hydrogen, of magnesium that I used, right? And again, remember it's 1:1. So therefore, it means the moles, the number of moles, let me rather use N. Therefore, the number of moles of magnesium that I used, okay, is also going to be what? 2.08 times 10 minus 3 moles. But why is that? Because for every 1 mole of hydrogen that I produce, I also use 1 mole of magnesium. Okay, so for every 1 there is 1. Okay, right, now please stay with me. So in this case, what do I want to do now? I want to now find the mass. So if I know the number of moles that I used of magnesium, then you agree with me, I can find the mass, right? So it means that number of moles would be mass divided by molar mass. Okay, so my number of moles is 2.08 times 10 minus 3, right? My mass is what I'm looking for, and the molar mass, you remember we found that in the periodic table. The molar mass of magnesium is 24, and in this case, all I'm simply going to do, say 2.08 exponent minus 3 multiplied by 24, and we get, okay, I get a mass of 0.05, sorry. So that's, let me just round it off to 0.05 grams. Okay, so it means that the mass of magnesium that I must have had before is 0.05. Okay, let me just check something here quickly. All right, something is not corresponding. Okay, let's just check there. Okay. Oh yeah, oh yeah, oh yeah. Ladies and gents, I'm very sorry about this. You see, mistakes happen to the best of us. Please, let's just go back to the question. Sorry about this, but I'm sure it will be quite a learning moment for all of us, right? Now look at this. I actually substituted time. I was given rate of reaction in moles per second. Okay, not moles per minute. Can you see that? So it means that this time that I have here, I was supposed to actually convert into seconds, right? So in this case, how do I convert 10 minutes into seconds? All right. So 10 minutes, so you'll say 10 multiplied by 60, right? So in this case, that would give us, okay, please remember, that would give us 600, isn't it? Okay. So please remember that. Ooh, I almost created a very, very serious mistake. So in this case, we said 10 multiplied by 60, that gave us 600. So in this case, instead of using, so instead of using seconds there, I used minutes, but please remember it's supposed to be 10, it's 10 minutes. Can you see? So that was 10 minutes. So our time was in minutes. So we're supposed to convert that to seconds, right? So that's 600. So it means that my moles, okay, the number of moles would be different. Okay, so now I'm going to say it's 2.08 minus 4, okay, that value there multiplied by 600, okay, so that's 0.1248 moles. Okay, I'm just not going to round it off here. So now what does it mean? It means that the number of moles of magnesium would actually be the same value as well. So that's 0.1248 moles. Okay, right. Now that we've got the number of moles of magnesium, so we're going to substitute that value there, 0.1248. Okay, so I'm going to take that value and multiply it by 24. Okay, and I'll tell you why I was able to pick that up. You know, that's very important, by the way. And I get the mass to be equal to 2.9952. You can just round it off to 3 grams. Okay, right. So I got the mass to be 3 grams. Very important. How did I pick up that there was a problem? Right. Note, when I looked at the values here on my graph, can you see that at a point my mass was 2.6 grams? Now it didn't make sense for the initial mass to be less than some of the mass that you have as it was decreasing. So in this case, it tells me whatever x is, whatever that mass is, it must actually be more than 2.6, right? So when I got 0.05, I just realized now there must be a challenge there. Sorry about the scratching out. Okay, so just remember that it was given to me in moles per second, so I was meant to convert time into seconds. I hope that makes sense. I hope you'll forgive me for that error, but I suppose it gives us a teachable moment as well, isn't it? Okay, right. So I want us to tackle another question, but let's finish off on this one. So the last thing that they ask us, they say use the collision theory to explain why the curve in experiment 2 is steeper than that of experiment 1. Okay, so they want us to explain why the curve in experiment 2, why is it that the rate of reaction in experiment 2 was much higher than that of experiment 1. Okay, so what are we going to say? We say an increase in the state of division. Remember experiment 2, that's what we did, right? will actually ensure that more collisions take place per second, isn't it? It means that there'll be more collisions that take place per second, right? That will increase the number of effective collisions, and as a result increase the rate of the reaction, right? So remember, we've increased the state of division. It means that more particles are able to collide, right? So it increases the number of effective collisions per second, and as a result the rate of our reaction. I hope that makes sense, ladies and gents. Let's go to the next question. Yeah, so I recognize the previous question was a bit of a challenge, but let's take the one from November 2020. All right, I want us to quickly have a look at it. All right, so they give us the reaction of calcium carbonate and excess dilute hydrochloric acid is used to investigate one of the factors that affect reaction rate. The balanced equation for the reaction is, okay, it's given there, that's calcium carbonate, 2 hydrochloric acid, forming calcium chloride, H2O, and carbon dioxide, okay? Right, so, by the way, just to quickly note some few things there, you already see how they told us that we've got excess dilute hydrochloric acid, right? So that simply tells us that in this particular question, what we're simply going to do is that we simply know that calcium carbonate is therefore our limiting reagent. What does that mean? It means that it will limit the extent of the reaction. It will be the one that runs out first, okay? Well, actually, it will be the one that runs out, okay? So as a result, because it runs out, the reaction will stop because we've run out of calcium carbonate. Can you see? Right, now, they say the mass of calcium carbonate is used in all the experiments, and the temperature of the hydrochloric acid in all experiments is 40 degrees. Right, now if you remember what I said to you in the previous example, right? So now they give us experiment A. They say, okay, the volume of hydrochloric acid is 500. Okay, they say the concentration is 0.1, and they give you there the state of division of calcium carbonate, that's granules, right? All right. By the way, okay, so that's granules. Okay, we'll come back to that. So it means it's in pieces. And then B, they tell us still the same amount of hydrochloric acid, same concentration, but this time it's in lumps, right? So lumps, it means it would be in bigger chunks, right? And then in C, so you would have that in powder form. You know, at this rate, ladies and gents, I also want to just highlight something that is a bit of an issue when it comes to the interpretation and the, when we have to answer questions in chemistry. The unfortunate thing is that most of the stuff that we deal with, for someone like me who's not a first language English speaker, certain words can tend to be problematic. So I just want to try and implore, to examiners, when they use certain language, they must actually make sure that it's accessible to anyone and everyone, by the way. I say that because, if you think about it, if you say granules and lump, to someone else, it might not be that clear which one is actually more divided than the other. So please, I just implore to those who are examining, who are drafting these questions, to always consider that. Right, now let's look at the question. Right, so now what's different? It's the state of division of calcium carbonate. Can you see that? So already, what is it telling you? That is going to be our, what we call our independent variable, okay? Now, and that's the first question that you asked, right? They say, for this reaction, write down the dependent variable. So what is that going to affect? It's going to affect the rate of reaction. So The dependent variable, as I said to you, will always be the rate of reaction. Okay, right. The independent variable, right, in this case, obviously that will be the state of division of calcium carbonate. So in this case, we have got that. Hope you've got that in the bag, right? Now, then they give us a graph. They give us a graph of carbon dioxide that is produced during experiment A. So it's this one here. They say it's collected in a gas syringe. So you can see we keep collecting a gas, and what happens as time progresses, the volume of that gas, okay, carbon dioxide, the volume of it keeps increasing. But then you get to a point where the graph or the curve kind of flattens, okay? Isn't it amazing talking about that during this time, hey? Right, so it kind of flattens there. So what happens when we get to this point here? So I want to actually now explain it in terms of what was said to us there. Remember they said calcium carbonate, or rather they said hydrochloric acid is in excess. So it means that calcium carbonate is the one that limits the reaction, right? So it means at this particular point, we ran out of calcium carbonate, and so the reaction stopped. That's why we couldn't produce any more carbon dioxide, okay? So it means the reaction reached completion at that state there, or at that stage there, okay? Right, now quickly let's look at the next questions. Okay, the questions that follow. So I will just apologize. I'll keep flipping between the two pages. Right, I hope you can see that clearly. Right, they say what can be deduced from the graph regarding the rate of reaction during the time interval 20 to 40 seconds. All right, so during that time interval between 20 to 40 seconds. All right, so want to know what is the rate of reaction doing there. Now you'll see that the rate of reaction here was increasing, isn't it? It was increasing quite steadily. And then what happens? The rate of reaction just begins to slow down, okay? So when that graph curves over there, it's actually slowing down. It's slowing down even more, right? Because the change is now decreasing, isn't it? Okay, and until we get to that point where there's no longer any change that's taking place. So between 20 to 40 seconds, the rate of the reaction is actually decreasing, okay? And then between 60 and 120 seconds, okay, between 60 and 120 seconds, what can we say about a rate of reaction there? Okay, it's 0, okay? In this case, why is that? Because the reaction has reached completion. So there's no longer any change in the moles over time. So the rate in that case has become 0. Okay, right. And then the next question, they say to us, calculate the average rate of reaction in cubic centimeters per second. Okay, so the average rate of reaction in cubic centimeters per second at which carbon dioxide is produced in the experiment. Okay, so we want to calculate the rate of reaction. So let's go to our graph again. Okay, right. Now, ladies and gents, because they want the average, I will actually start from the beginning and end where the reaction stops. That's at 60 seconds, isn't it? Right, so let's calculate that average rate of reaction. So I'm going to say, so the rate of reaction, let me just write in a different color there. Right, so the rate of reaction, okay, so my rate of reaction there will be equals to the change. Now please note, they said they wanted it in cubic centimeters per second, isn't it? Okay, so now I know it's the change in volume, and the volume of what? Carbon dioxide. So it's the change in volume of carbon dioxide divided by the change in time. Okay, so what is my volume final? So remember, so that's going to be volume final minus volume initial divided by time final minus time initial. right? So that's the change in volume divided by change in time. So my volume final, okay, it's that value there, 500. So our final volume is 500, but what about our initial one? Our volume initial was 0, okay, divided by what was the final time, right? And this time, okay, we are quite fortunate, it's in seconds. They wanted it in cubic meters per second, so in this case we know that time is in seconds, so that's 60 minus what was our time initial again, that would be 0. Okay, so all that we're simply going to do is put that in our calculator, okay, and find that value there. So we're simply going to say that is going to be 500 divided by 60, and the value is 8.33. Okay, so that would be 8.33. That's going to be cubic centimeters. Remember, our volume is cubic centimeters and our time is in seconds, so per second, that's -1, right? So that's cubic meters per second. All right, let's go to the next question. Okay, so then they say, how will the volume of carbon dioxide produced in experiment B, all right, so there's our next question. So how will the volume of carbon dioxide produced in experiment B compare to that produced in experiment A? Choose greater than, smaller than, or equal to. Now please, I want you to note, ladies and gents, in experiment B, there is absolutely nothing that changed except the state of division. Can you see that, nah? Right? So in this case, there is absolutely nothing that changed except the state of division. So the amount or the mass of calcium carbonate is the same. The volume and the concentration of the of hydrochloric acid remains the same. So it will also mean that the volume of carbon dioxide that is produced will actually be equal to. Now please, I don't want you to confuse two things. The rate at which we produce would be different, okay, but the amount of gas that you produce would be the same. So that is why, if you kind of think about it, okay, maybe we'll get to that in a little while. Let me not get ahead of myself. Okay, so the amount would be equal. Why? Because you've got equal masses, you've got equal volumes and concentration of your hydrochloric acid. Okay, so the answer there would be equal to. Okay, they say now that's 5.5. A graph is now drawn, okay, for experiment C, okay, on the same set of axes. How will the gradient of the graph compare to the gradient of the graph of experiment A? All right, so graph of experiment C, I want you to just remember, in experiment C we were using powder, isn't it? So in a sense, when I use powder, it means that I'm going to reach completion faster than I did in experiment A, for instance, or experiment B for that matter, right? So the graph for experiment C would actually be a graph that looks more or less like that there. Okay, it would have a higher or a steeper gradient. Okay, so they wanted you to compare the gradients. So in this case, we would say it would be greater than. Okay, right, so that would be our graph there. In fact, why don't we just draw the two graphs, right? I'm just going to try and so let's just copy the graph for experiment A over here, and let me show you what the one for experiment C would look like. So if that graph looks like this, so this is for experiment A, where we were using granules, right? So now what would the graph, remember we reached 500, okay, cubic centimeters within a space of 60 seconds. Okay, right. So now, what would the graph actually look like if now I'm using powder, right? It means the rate would actually be much faster. So I would reach the same amount. You remember what I was saying to you earlier on, right? We still reach the same amount, 500, because we've got equal reactants, equal volume, and equal mass of calcium carbonate in this case. So you'd have a steeper gradient for reaction C. So this would be the graph for reaction C, and it's showing you that the rate would be much faster. How do you know that the rate is faster? Because you reach completion much sooner than you did in the first one. Can you see? So this shows us that the rate is higher. Obviously, if we had a lower rate, then you'd have something that is below here. Right, now let's get to the last part of the question. All right, as we conclude, okay, with our battery running low. Okay, so right, so now they say to us, okay, so they say a graph is now drawn for experiment C. Okay, so I've kind of lost my place there. So we did this one, we did this one. All right. So they said we should use the collision theory rather, to fully explain. Okay. So we said the gradient would be greater than. So we should now use the collision theory to explain why that is the case. And we explained it earlier, right? We said in this case, the greater the state of division, or in this case, the more finely ground it is, right? The greater the state of division. In this case, the more collisions take place per second, okay? And that will actually result in the rate of reaction increasing. Okay, so in this case, the greater the amount of the greater the state of division, the greater the amount of reactants or products that are available to react. Okay, more collisions per second take place, and as a result, the rate of reaction would increase, isn't it? Okay, so last part, they say, assume that the molar volume at 40 degrees is 25.7. So you remember that Vm value that we had earlier on, right? So I'm just going to move this a little bit. So that Vm value, so they're giving us that Vm is actually 25.7 cubic centimeters, or cubic decimeters rather, per mole. Okay, and they say calculate the mass of calcium carbonate used in experiment A. All right, so calculate the mass of calcium carbonate used in experiment A. Now, one thing I want to remind you of, right? We already have a graph that kind of tells us about the volume of carbon dioxide. So we didn't know much about calcium carbonate, right? But what we do know is that we are given the volume of carbon dioxide. Okay, so what do we know? We know that, first of all, we can find out the number of moles. Remember, I said to you, when you use this, you can only use it with the number of moles, isn't it? Right? So now what I want to find out, okay? So then I will say, okay, we want to find out what are the number of moles, right, of carbon dioxide. So that's going to be volume. So how much did we form? 500, okay, divided by, what's the molar gas volume? It's 25.7, okay? So let's find that out quickly. So that's going to be 500 divided by 25.7, and we get a value of 19.45. Yeah, let me just say 19.55. Oh, yeah, once again. Oh, ladies and gents, Yeah, today isn't such a a great day for science. Hey, right. Please note that this volume here should be in cubic decimeters because our molar gas volume is cubic decimeters per mole. So now my volume in the table was given in cubic centimeters. Can you see that? Right? So now I need to convert that to cubic decimeters. So I'm going to say, okay, this is 0.5. And where did I get the 0.5? Because if I say 500 divided by 1000, okay, that will give me 0.5, isn't it? So it's going to be 0.5 divided by, what is my so that's 25.7, my molar volume, right? So that's 0.5 divided by 25.7, and we get, okay, so that's 0.019. Okay, all right, if you want to, you can say 0.0195. Okay, and those are the number of moles of what? Remember, that's the number of moles of carbon dioxide that is formed. But what do we know about this reaction? It says for every number of moles that I produce of carbon dioxide, I would have used the same number of moles of calcium carbonate. How do I know? For every one, there's one, isn't it? So it means for every amount here, it will be the same amount there. So what's the number of moles of calcium carbonate? It should actually be the same number. So the number of moles of calcium carbonate, okay, would be equal to 0.0195 moles. Okay, right, so those are my moles for calcium carbonate, isn't it? Right, so they should be the same as the number of moles for carbon dioxide. Right, and then just the last part. Now we want to finish off this last part. Remember, what they asked us is to calculate the mass of calcium carbonate. I'm sure you've got this by now, right? So how do we get the mass of it, right? So I'm going to say number of moles. That's going to be mass over molar mass, okay? So that's 0.0195, which is equal to mass divided by. Now, how do I get the molar mass of calcium carbonate? You go back to your periodic table, isn't it? Okay, so calcium, right? If you check in your periodic table there, all right, I want you to know how to navigate your way around it. So calcium, okay, there it is. It's got a molar mass of 40. So you've got 40 plus, you are adding the molar mass for carbon, that's 12, okay, plus the molar mass for oxygen. But how many atoms of oxygen do you have? You've got 3, so that's 3 times 16. When you add all of those up, that will give you 100. So the molar mass of calcium carbonate is 100. You can do that yourself, ladies and gents. So in this case, all I want to do is to get the mass. So let's multiply that by 100, and what we will get is the mass is 1.95 grams. Okay, right, I hope that is quite clear. You know what I want to do? I want to leave this lesson here on rates of reactions. Okay, so what we'll do is that we'll come back to this section. When you've got more questions, by the way, you're more than welcome to send me those questions. But I want to leave it here, and then we will do more questions when we actually do our revision. We'll come back on this section. So I hope that was helpful. Okay, please just tell me. Of course, we made a couple of mistakes today, but don't worry, every dog has its day, right? Okay, so thank you again for watching. We'll see each other again. All right, I'll be covering another section. I'll see if perhaps I need to do some more questions based on the feedback that I get from you. All right, please, you're more than welcome to send me an email, mlungisi.m.ngosi And please don't forget to hit that subscribe button. Until then, we'll see each other again. Thank you. Sharp, sharp.